In the last part of this lecture on sampling and reconstruction, we are going to cover a bit better the relation between x star of S and x of Z. So we have seen that there is a one-to-one relation established by replacing Z equal to e power st. However, while the relation between the function is one-to-one, the relation between the points in one plane is not one-to-one with the points in the other plane. In particular, what happens is that multiple points in the S domain are mapped to the same point in the Z domain. This can be seen in the following way. Let's assume that S can be written in this way. So S is a complex number, so we write it as a real part plus J imaginary part. So if if Z is equal to e power st, because we are doing this replacement over here, then what we obtain is that e power t multiplies sigma plus j omega. This can be written as this exponential times this exponential. We note that this exponential here is an absolute value because it's a function that is always positive and is a real function. This function here instead is a function that is imaginary, and in particular is a function that has absolute value equal to 1. So in particular, we notice that we can rewrite this in this way. So to omega, we can add 2k pi over t, and we see that adding this will not change z. So let's look this at the board if this is not clear. E power sigma capital T times e power j capital T omega plus 2k pi over t can be written as e sigma t times e j capital T omega times e power j, and then this capital T and this capital T simplify, so we have 2k pi. And this number is actually equal to 1. So we see that this number is actually equal to this number. So this is basic theory of complex numbers. But the implication of this is that multiple points S, so all the points that are described in this way, are actually mapped in the same Z, in the same value of Z. Okay? So in particular, which point? So the points in the S-plane that have angular frequency which differs by an integral multiple of omega s, where omega s is the sampling frequency 2 pi over t, these are mapped into the same point in the Z-plane. So let's look this with an example. So we consider 2 points, okay? So the points S1 that is given by minus sigma plus j omega, and then the points S2 that has the same real part, but the imaginary part is omega plus 2 pi over t. And now we want to map these 2 points in this plane. So let's do this, okay? And we see that Z1 is equal to e power minus sigma t e power j t omega, okay? And Z2 is equal to e power minus t sigma e power j t omega plus 2 pi over t. And we have just shown that actually this is equal to e power minus t sigma e j t omega. And this is equal to Z2, okay? So this means that here there exists a point Z1 equal to Z2 towards which both points S1 and S2 are mapped, okay? This means that there are infinitely many values of S for each value of Z. Now, knowing that there is this issue, what we want to study is if stability is preserved, and also how points and some particular characteristic of the S plane are mapped in the Z plane. So let's start to look at the problem of stability. So if we are in the S plane, so we know that values of poles that happen on this side are good for stability. Poles that happen on this line are on the margin of stability, and then this part of the plane is actually the part of the plane that corresponds to instability. So we have, now we sketch the absolute value of z. So the absolute value of z is equal to the absolute value of e power t sigma, e power j t omega. And as we said, these have absolute value 1, so this is e power t sigma. We can drop the absolute value because this is always a positive number. So these correspond to this function over here, where here on this axis we have t sigma, and on this axis we have the absolute value of z. So here we have 0. And we see this, that for sigma less than 0, okay, we have that the absolute value of z is less than 1. And for sigma greater than 0, then we have the absolute value of z is greater than 1. And when sigma is equal to 0, then we have that the absolute value of z is equal to 1. So this means that if this is the S plane, so this is the S plane, okay, and we have that this is the good part of the plane, this is the margin, and this is the bad part of the plane, then when we are in the z domain, we see that the values of sigma with the negative real part correspond to the values of z that have absolute value less than 1. So in the complex plane, these correspond, oh, sorry, I used the wrong color. So this correspond to the inner part of this circle. Then if instead we look at the margin, so when sigma is equal to 0, then the absolute value is equal to 1. And so we have that this corresponds to the circumference that has radius equal to 1. And then we see that when sigma is greater than 0, then the absolute value is greater than 0, and so we are outside the circle. So this is how the planes, the semi-planes, the negative semi-plane, the positive semi-plane, and the imaginary axis are mapped in the z plane. Okay? So this covers these 3 points, and then we want to also try to understand how the phase is mapped. So up to now we talked about the real part of S, and now we want to see what happened to the phase of Z. Okay, so the phase of Z is omega t. So this is due to the fact that here we have that Z is equal to this product. So the phase of this is T omega. Okay, so omega capital T. So this implies that when omega goes from minus omega s divided by 2 and omega s divided by 2, then the phase goes from, the phase of Z goes from minus pi to pi. Okay, so let's show this at the board. So we want to say what happens if omega is equal to minus omega s divided by 2. Okay, what happened to the phase of Z? So the phase of Z, we said that is omega t. So in this case is minus omega s divided by 2 times t. Now, if you remember, omega s is actually defined as 2 pi over t. Okay, so if we replace these in here, we get minus the 2 and 2 simplifies, the t and t simplifies, and we get the pi. Okay. If instead we have that omega is equal to plus omega s divided by 2, well, we know that we repeat this computation and we get that the phase is equal to plus pi. Okay? So this implies that we can actually identify and partition the S-plane into horizontal strips that are width equal to omega s, okay? Because they go from minus omega s divided by 2 to plus omega s divided by 2. This is represented in this graph over here. And we call this strip of plane, so the plane that goes from, the semi-plane that goes from minus j omega s divided by 2 to plus j omega s divided by 2 as primary strip, okay? And then we identify these other strips, so this one, the one after that, and so on, and this one and the one below, this one and so on, as complementary strips. So these are strips that again have width that goes from width equal to omega s, and this particular one goes from j omega s divided by 2 to j3 omega s divided by 2. So this is basically explained over here, and the point is that as we have shown, everything that happens outside the primary strip, so if here we have a point that is outside the primary strip, this will be mapped into the primary strip, okay? So the primary strip is that strip that is mapped one-to-one with the z domain. So if a point appears in the primary strip, that is mapped to a point in the z domain. And all the points that appear in the primary strip are mapped to different points in the z domain. The problem is that if then we have points that appear in the in the complementary strip, those points are mapped to the same point appearing in the primary strip. So this what implies? Well, this implies that if we have a system, okay, so let's have a system, and let's define here the primary strip. So this is the primary strip, and these are the complementary strips, okay? And we are sketching the root locus, okay, or we are placing the poles, okay, of this function. And let's assume that the poles are here and here. Okay, so these two poles will be mapped, okay, inside this circle. That's fine. But what happens if then we also have poles here and here? So outside, so this is the primary strip. So if we have poles that happen outside the primary strip, what happens when we map them here is that they will be mapped to points that actually correspond to these poles. Obviously, these poles are not actually there, okay? So these are fake poles. But what happens is that if we go from this to the z-plane and then from the z-plane back, we don't know if this pole is here or is here, okay? Because these 2 points are mapped in the same point in the z-plane. So this is telling us that we have to be careful when we choose the sampling time, because the sampling time obviously is linked to the width of this primary strip, because the width of the primary strip is omega s, and we see that omega s is 2 pi divided by t. So what we want is that the primary strip is large enough to include all the poles that appear in our system, okay? Because if it's large enough, if we know that the sampling time is small enough such that omega s is large enough that the primary strip includes all the poles, then we know that what we are seeing here is actually all poles belonging to the primary strip. If instead we are in this situation in which we have chosen the sampling time not small enough, so the sampling time is big, we have this omega s that is small, then we are in a situation in which we know that actually we are not sure the point that is mapped here if it actually belongs to the primary strip or not. Why this is important? Obviously because we have to know the position of the poles to do some certain type of controls, okay? This is also a different way to state the Shannon theorem. So this is again a limit on omega s. If the Shannon theorem says that omega s has to be greater than 2 times the maximum frequency appearing there. Now, the maximum frequency in a system is actually linked to the poles. So what is saying that this omega s has to be 2 times omega x. So it has to be basically, if this is omega x, this omega s has to be 2 times omega x, so that we are actually in this situation in which the primary strip includes all this part, and we can distinguish between the points. Okay, so this is another way to state the Shannon theorem. Let's now look at how various points and characteristics are mapped in the Z domain. Okay, so here we have, let's start with the points in the S-plane, and we start with the point 0. So where the point 0 is mapped in the Z-plane? So the point 0 is a point which has real part equal to 0. So when we compute the exponential of sigma t, that will be the exponential of 0, that is actually 1. And then the phase of this obviously is actually 0, so the omega is 0. So when we compute e power j omega, that's again 1. So actually this point is mapped to, in the z-plane, to the point equal to 1. Then what happens instead to points that are actually going towards minus infinity? Well, this can be explained easily. So we have sigma goes to minus infinity, z is equal to e power j, e power sigma capital T times e power j omega capital T. Now, since this sigma is going to minus infinity, this exponential is going to 0. So actually this is going to 0. This also means that it doesn't matter the phase, okay? The phase can be whatever, okay? This is going to 0 because the absolute value is going to 0. So if we look at this, we see that this point is mapped to 0, but also this point is mapped to 0. And any point here that is actually going to infinity is mapped towards 0, okay? Then let's look at these 2 points over here. So these points are on the imaginary axis, and we saw that the imaginary axis is mapped on the circle. So which point of the circle? Well, we saw that the point corresponding to j omega s divided by 2 is mapped in plus pi. So this will be mapped in e power j pi, so here, or minus pi is the same point, so they are mapped in here. The next set of characteristics that we see are constant attenuation lines. So constant attenuation lines are vertical lines in the S-plane. Why these are important? These lines are important because we know that if, for instance, we fix this line, all the poles that belongs to this side will produce a response that is lower than the poles that are on the left side of this line. So the constant attenuation line is telling us what happened to points, to poles that produce a response that has the same speed, okay? Because all the poles that appear here produce a response that have the same speed. So as we can imagine, these actually correspond to circles. We already saw a constant attenuation line, and it's the imaginary line. And the imaginary axis actually is mapped to the circle of radius 1. Then this means that constant lines, vertical lines that are on the left-hand side of the imaginary axis will be mapped inside the circle, and constant lines that are on the right-hand side of the imaginary axis will be mapped outside the circle. Okay, so also this is intuitive. The next characteristic that we look at is the constant frequency lines. So what happens, instead of considering vertical lines, we consider now horizontal lines. So horizontal lines are lines in which the sigma values changes, but the omega values doesn't change. So this means that when we map it to the z-plane, the phase stays the same. So if we look, for instance, at this line, this is mapped here because the phase is constant, so we have a straight line where the angle is obviously the same. What changes is the value of the point on the line. As we go towards minus infinity, we are going towards 0, and as we are going towards plus infinity, then we are going outside the circle. Okay, so also this is not difficult to understand. This is basically the last characteristic that we look at, and is the constant damping ration line. To explain this, we need to use the board. So here we have the point S, and we parameterized up to this point, the point S, as sigma plus j omega. In this case, we want to parameterize this point using a different notation. So we write that the point S is equal to zeta omega n, so this symbol that is also on the slide is called zeta, plus j omega n square root of 1 minus zeta squared, okay? So we use this parameterization where obviously this term is equal to sigma, okay? And this term here is equal to omega. In this case, we use omega d, okay? Just because this has this name in this case. So we have this parameterization. Why we want to use this parameterization? First of all, is basically the same thing, because here we are using a parameterization in which S has two values, two parameters, that is sigma and omega d. And also here we have two parameters. The two parameters are zeta and omega n, okay? So these, choosing zeta and omega n, we can obtain the same values that we can obtain choosing different values of sigma and different values of omega d, okay? Why we want to use this parameterization? Because it has a geometric interpretation. So this parameterization means that the base of this triangle, so let's consider this triangle here, the base of the triangle is equal to this expression, and the height of this triangle is equal to this expression over here. Why? Because this is actually equal to omega n. Okay, so you can compute this omega n using Pythagoras theorem. So the square of this plus the square of this, you take the square root and you actually get omega n. Why this is a nice interpretation? Because it can be proved that sigma is actually equal to the inverse cosine of zeta. Okay? How do we prove this? We use the theorems of triangles, and we see that, for instance, this value here, okay, can be computed as this times cosine of theta. So C omega n is equal to omega n cosine of theta. This and this simplifies, and you see that we have found this relation. So this means that if we keep zeta constant, then we are keeping this angle constant, okay? So this is a constant damping ration line, so a line that goes in this way, grows in this way, so the angle in the S-plane is constant because zeta here is kept constant. So if we compute the absolute value of z, we obtain this expression, and if we compute the phase of z, we obtain this expression over here. And in this expression, what we are keeping constant is zeta. What is varying is omega n. So we see that the absolute value behaves as a decreasing exponential, and the phase is actually behaving linearly with omega n. Or the rest is constant, so omega n is actually moving, and is moving as a linear function. So this will create, in the z domain, what is called a logarithmic spiral. So something that is moving in the phase version as a linear function, but the absolute value is decreasing exponentially. So it creates this very nice spiral. Finally, we have this diagram. So this diagram here is plotting various characteristics. In particular, these are parameterized in zeta and omega n, so it's this one, okay? And it's plotting the constant damping ratio lines, so these diagonal lines here, that we know they correspond to spirals, so there are lines that go towards 0 in this way. In this plot, what is plotted is only the first half part of the spiral. So it's just the part that goes from this point to this point, because otherwise there will be too many points, too many lines, and you wouldn't understand what is going on. So this is just a part of the plot. What else is plotted here is also these circles here. So these circles is the circle obtained when zeta is moving and omega n is kept constant. And this circle have a parameterization that is not, we are not looking at. But if you plot it, if for instance you use MATLAB and you plot it, you will see that will produce this line over here. Okay, so this one and so on. So why this is interesting? Well, this is interesting because we can see that one characteristic is preserved when we go from this plot to this plot. If we look at these two lines, so the diagonal line and the circle, they are intersecting, and in particular, they are perpendicular to each other, okay? What happens is that it can be shown that also these lines are perpendicular to each other. So even though you see that these lines are very deformed when you go to the z-plane, the fact that they are perpendicular is preserved. And this is a type of transformation that has nice mathematical properties. With this, we conclude the lecture about sampling reconstructions. We have seen various different topics in this lecture. The first part of the lecture was about trying to find a mathematical description for the interconnection of a sampler device and a hold device. And we have found that the scheme can actually be represented using the starred Laplace transform and the Laplace transform of the hold device. Then in the next part of the lecture, what we have seen is to study better the meaning of this starred operator, this function Laplace starred, so this starred Laplace function. And we have seen that using this we can prove the Shannon theorem, and we can try to avoid some distortion when we use sampling. Then the following topic that we have seen is actually the topic of studying the zero-order hold and the first-order hold and how they behave, and also the fact that they introduce problems in our analysis. Finally, the last topic that we saw in sampling and reconstruction is how the S-plane is mapped in the Z-plane. So this lecture is quite dense. It has a lot of topics, but it's actually instrumental then for the rest of the course.